Uh-oh.
Good morning.
Okay, this is Dr. B, and it's topic 3.2, properties of solids. There's four types of solids. We've got ionic solids, you might call them salts. Molecular solids, for example, carbon dioxide, dry ice in the solid form. These are covalent substances. Metallic substances like a chunk of copper or iron. And finally, a little bit less common are covalent network solids, things like diamond and glass. Covalent substances that show a continuous lattice, oftentimes with very strong bonds between them. Okay, let's take a look at each one. Let's start with salts, otherwise known as ionic solids. Here's what they might look like. Notice this continuous lattice of cations and anions. These could be +1, -1. They could be +1, -2, things like that. Don't forget that when you add these to a solvent, they may dissolve. If you throw them in water, they may separate into a dissolved solution. This is sodium chloride shown here. We've got the sodium cations and the chloride anions. In terms of their properties, they will have very high melting points and boiling points. You could put sodium chloride in a direct flame. It won't do anything. They will only conduct electricity when they are fluid, meaning in the liquid or gaseous or dissolved state, but not as a solid. You need to have the electrons or the ions to be mobile in order to have this conductivity. Notice they're also very brittle, so that if you apply stress to one part of it, sort of hammering on it, you can go from all attractive forces to all repulsive forces along this line here. See, red, red, blue, blue, that sort of thing. And you'll end up forming a crack, right? You'll form oftentimes very linear sort of cracks in these systems. So they're brittle. Molecular solids are just covalent substances that are in the solid form. So they will also form a crystalline structure. They have individual molecules, but things are cold enough that they are locked into place. It's a combination of covalent bonds and intermolecular forces. They're in the solid phase. In terms of properties, the melting points and the boiling points will be way lower because you have, in this case, not an ionic bond, but you'll just have intermolecular forces between covalently bonded substances. In terms of conducting electricity, they do not, because you don't have any ions to speak of, period, and you don't have mobile electrons. An example might be carbon dioxide in the solid form. Metals are very common, metallic solids. So here you have a continuous lattice of those atoms, not ions, but atoms. And of course, an atom consists of a nucleus surrounded by electrons. So you do have plus to minus built into that. And with metals, they're strong. They're strong enough that that's all you need. These electrons are considered to be very mobile. This is why they conduct electricity so well. The electrons are not necessarily held to a specific atom. It also explains why the boiling points and the melting points can be relatively high, but consider things like gallium and mercury and others. They're not necessarily all high melting points. Some metals are actually liquids at room temperature. Because those electrons are 2,000 times smaller than the nuclei, they can squeeze in between so that you almost always, even if you apply stress to this thing, will have a plus-minus relationship. So metals are generally very malleable, meaning they can be smushed, and also ductile, meaning they can be pulled into a wire. Covalent network solids are perhaps the most interesting form of solids. Here you have covalent substances with some metallic-like properties. They're covalently bonded. You have a 3D network. There's not a whole lot of them, but boy, they can be very strong substances. Diamond is an example where you have a tetrahedral lattice of carbon atoms, and that's it. Silicon dioxide, sometimes referred to as glass or sand, is another one. And what you're looking for is a continuous lattice in the covalent type, leading to some very strong properties. The melting points and the boiling points can be very high, right? Silicon dioxide typically won't be melted with a flame, for example. The conductivity in the solid state is going to be on the low side because you do not have mobile ions or electrons. So glass is oftentimes used as an insulator since it doesn't conduct electricity. Take a look at telephone pole lines and you'll see these giant glass insulators. Graphite is a unique case because although it is organic, I mean it is pure carbon, it's found that it actually does conduct electricity. Imagine these individual sheets of sp2 hybridized carbon atoms that are hexagonal with these very weak dispersion forces in between. So weak that these things are sometimes used as lubricants, solid lubricants. So in the solid state, you have excellent conductivity. You know, it makes you wonder what you could do with that. And people are starting to investigate things like individual layers of these graphite molecules known as graphene. And it's those should be alternating double bonds there, showing that the carbon is sp2 hybridized. Okay, it's time for some questions. Identify the following types of solids. Pause the video if you need to. Lithium nitrite. Sounds like an ionic compound to me. Nickel solid. Hey, there's just one thing. It's a metal. Must be metallic. Carbon tetrachloride in the solid form. Boy, I think you'd have to freeze that down pretty cold. Looks very organic. I guess we have a molecular solid. I think of it as a covalent solid. Beryllium sulfide. This is an ionic compound. Silicon carbide. Now, wait a minute. Silicon's not quite a metal, is it? It's not. This is not going to be an ionic compound, probably. I wonder if this is an example of a covalent network solid. Notice that I deduced that by noticing that this thing has a semi-metal in it. A lot of them have that. Pure fluorine in the solid form. Well, it's right of the staircase. I guess this is a molecular solid. Oh, just based on the shape. AP likes to do this, by the way. This looks like red oxygen and some white hydrogens, things like that. Almost reminds me of just water molecules, right? So what type of solid would that be? This is a molecular solid. You know, it's an example that doesn't have carbon in it, but it certainly doesn't have any metals either. So molecular solid there. This looks like diamond to me. I believe that is a covalent network solid. Just all carbon tetrahedral. I just recognized it. Now, what are we looking at here? Is this a salt or something else? Careful examination reveals to me that I believe we're dealing with atoms. Atoms that only seem to have one valence electron, or maybe one electron at all, right? And so this looks to me like we're talking about metallic. And here, this is a typical representation of cations and anions. In this case, the anions are a little bit larger. This looks like an ionic compound. Good questions. Okay, which of the following could be the identity of a solid that is malleable and conducts electricity as a solid? Take a look at it, see what you think. Well, if it's malleable, that must mean that it is likely like a metal and it conducts electricity as a solid. Metals do that too. Salts don't. So I think we're just looking for a simple metal, and the only one is scandium right there. And there we go. Which of the following could be the identity of a solid that has a low melting point? Maybe it's molecular. Poor conductor of electricity. I'm still thinking molecular, so something that has no metal present. Zinc's a metal, boron's a metal, magnesium's a metal, but PF3 is a molecular solid, so I'm thinking the answer is probably B. A student finds a bottle of sulfur dioxide and hypothesizes that the solid is a good conductor because it's a molecular solid, has weak intermolecular forces. The electrons are therefore not held tightly to the molecules. Do you agree with the student's reasoning? Explain your answer. Doesn't sound that great to me. SO2 is not going to be an electrical conductor because covalent solids like this, molecular solids, don't conduct electricity. There's no electron flow. There's no movement of the ions. And they have having weak intermolecular forces. I'm not sure what that has to do with conductivity at all, right? So I do not agree with that student's comments. Okay, this is Properties of Solids, and this is Dr. B.